What is universal molding? Universal molding, also known as MU, is an injection molding process optimization discipline. It was developed with the collaboration of the Caribbean plastic industry and academia, the University of Puerto Rico in Mayagüez. The old focus on plastic part production, focusing on production volume, without taking into consideration neither the minimization of resources nor the maximization of quality. This had to change because of client demands, increase of operational costs, and global competition. The new focus of production, using process optimization methods proven by means of organized and scientifically backed molding techniques. MU combines technical and scientific backgrounds in order to increase process efficiency, decrease product costs, and shorten manufacturing cycles. Some of the techniques used are injection machine rheology, approximated rheology, and design of experiment, or DOE. Injection machine rheology is an effective, proven technique used to determine injection time. The graph shows the effect of injection time on power by volume, where the area below the curve represents the percentage of energy consumed for each decrement in injection time. Note that power consumption increases when injection time decreases. This graph shows that the power required at higher injection rates is considerably high, or the power consumed by the injection unit is more significant at lower injection times. The idea is to select an injection time in the zone in which time stops contributing as power increases. A similar graph is that of viscosity versus shear rate, in which the viscosity of the melt decreases with an increase in shear rate. This behavior is called shear thinning. Approximated rheology. Developing a rheology laboratory with an injection molding machine consumes time and resources. With approximated rheology, a mathematical prediction technique, the laboratory can be achieved in less than a third of the time. The graph below of viscosity versus shear rate compares the two methods, using conventional machine rheology and using the approximated method.
In a process optimization laboratory, which of the two methods should I use, conventional or approximated?
Approximated is the method preferred by universal molders, though both processes conceptually function the same. The difference is that using mathematics consumes less time and resources.
Is there an equation that can determine injection time?
Yes. Injection time is determined by means of a prediction equation and not by means of personally determined criteria or graphic interpretation. While developing universal molding, it was established that each parameter should be determined by means of clear procedures and equations. This was done in order to guarantee similar results between universal molders. Design of experiment, DOE. DOE is a powerful and effective statistical technique used for process optimization, which is combined with MU to predict the contribution of various effects, such as shrinkage. Effect is a function of pressure, temperature, and time.
What do I need to know to perform a DOE?
Simple algebra. One of the established rules of MU is utilizing simple methods with clear procedures that function. Because of this, it is recommended using simplified DOE models, lineal equations with a maximum of 3 factors, parameters, and 2 levels, high and low. This is only possible if the designer satisfactorily understands the universal molding procedures, or whatever other scientifically proven discipline that is used.
Why should I know an injection molding discipline before creating a DOE?
It is recommended since injection molding processes have multiple process parameters. During a study of an effect, the list of possible candidates that may cause that effect could be reduced, if you understand each parameter's contribution. If not, the prediction can turn into something extended and tedious, with results that are not necessarily the best.
If the behavior of polymers is not lineal, why should I use lineal equations?
Simple. Nonlineal behavior can be analyzed if the range studied is sufficiently small. Consider the nonlineal effect illustrated in the graph. Between range AB, behavior is assumed to be relatively lineal. The basic stages of the injection molding process: injection, changeover, pack hold, gate freeze, cooling, plastification, injection. In this injection stage, the mold should be filled to between 95 and 99% of its total volume. The injection unit acts as a piston that forces melt from the injection unit into the mold. At this point, filling occurs with a rapid injection flow that should include the best melt properties.
What type of properties?
The best properties could be no burns, no flow lines, no degradation, minimal concentration of stress, etc.
What happens if the flow is slow?
When hot melt enters the mold, it comes in contact with the mold's cold walls and quickly thickens until it solidifies. Filling slowly increases the melt's density, or viscosity, and could end up creating difficulties in filling the mold, even prematurely solidifying the melt before the mold is filled. This stage is known as the injection speed control stage. Changeover. Changeover is when the injection stage ends. Once the injection unit is filled more than 95%, the injection stage ends and the pack hold stage begins.
How does the injection unit know that more than 95% of the mold is filled?
The injection unit comes with a lineal encoder that measures injection displacement.
Why doesn't the mold fill 100% during the injection stage?
There are various reasons. Let's look at a couple. It could cause flash on the molded parts. What stops the screw is the melt in front of it. Trying to stop it at exactly 100% without opening the mold would be difficult. Trying to fill a mold to 100% at a high speed could create a bounce-back effect on the screw. Plastic melt is compressible and during injection is placed under pressure. This pressurized melt can act as a compressed spring, pushing the injection unit backwards and causing a suck-back effect that pulls back part of the melt that was injected. Another reason that it shouldn't be done is because of material shrinkage. Melt occupies more space than solidified material. Once the melt enters the mold, it will cool and gradually shrink, leaving space for more material. Pack hold. In this stage, the screw continues moving like a piston, forcing more melt into the cavities until it fills the remaining portion that could not be filled during the injection stage. Without opening the mold, the injection unit compresses the melt, packing more material into the mold until the cavities are completely filled. During this stage, we achieve the proper weight for the molded parts, or what is known by universal molders as mass dimensions. Mass dimensions are those which are only a function of material quantity and should not be confused with dimensions that are due to shrinkage.
What parameter control is measured in the pack hold stage?
In this stage, the universal molder manipulates the compacting pressure.
Can this pressure control part shrinkage?
Shrinkage is controlled during the cooling stage. As mentioned before, while in the pack hold stage, we only control mass dimensions, those dimensions that are a function of material quantity. Gate freeze. While holding, the parts are pressurized until the material in the gates solidifies, creating a seal that keeps the melt inside the mold cavities. Let's look at the spaces that the plastic occupies in the mold. The gates are the small openings through which the melt enters the cavities. The melt enters the mold through a sprue and travels through the runner until it reaches the gates of the cavities. Normally, the gates are considerably smaller than the runner. The melt is forced through the narrow openings of the gates until the cavities are filled. The melt is then held inside the cavities until the gates solidify.
What would happen if I removed the hold pressure too soon?
The melt would return to the runner and even to the injection unit.
What happens if holding occurs for a longer period than is necessary?
If hold time is very extensive, the molder ends up molding runners.
How does the screw act like a piston?
This is achieved with a check ring that floats between the screw tip and the screw. During injection, this check ring moves against the injection unit, creating a seal and keeping melt from returning to the screw. During injection, the pressure in front of the check ring is greater than the pressure on the screw side, causing the check ring to move against the screw to create a seal.
Are there screws that don't have a check ring?
Yes, rigid PVC is very sensitive to friction between melt and a check ring. It is common to see that this type of system does not use one. Instead, this screw comes with an anti-rotation mechanism so that it won't rotate because of excessive pressure from the melt. Cooling. In this stage, heat is removed from the parts so they can be demolded with acceptable thermal dimensions. Thermal dimensions. These are dimensions that are a function of shrinkage and not a function of packed mass. The molecules of thermoplastic melt are in continuous movement. As they cool, they look for conformity and occupy less space. The goal is to stop molecular activity and manipulate this shrinkage to our advantage. Cold molds and an extended cooling time cause thicker walls. Hot molds and a shorter cooling time cause thinner walls. Thermal dimensions, as well as some mechanical properties, are a function of cooling rate. These mechanical properties can include stiffness, translucency, crystallinity, etc. Plastification. In this stage, the screw reloads with material for the next shot. The most important objective is to consistently produce a homogeneous melt. During plastification, the check ring moves and permits melt to pass to the front of the screw. Melt accumulates in front of the screw and causes it to be pushed backwards. Plastification occurs at the same time as the cooling stage. Under normal conditions, plastification finishes before cooling does. If for some reason cooling finishes before, the control will not allow the mold to open.
If permission to open the mold is denied, will the cooling time be extended?
Yes, it will alter the thermal dimensions.
What happens if the mold opens during plastification?
The melt inside the injection unit will drool into the mold. During plastification, this melt is pressurized. What keeps it in the injection unit is the filled mold. As a general rule, plastification should end around 1 second before cooling does. Permission to open the mold during plastification can only occur when the injection unit comes with a shutoff nozzle. It is important to know that the injection unit uses two sources of heat to melt the plastic: heater bands and friction. Another general rule is 20% of the heat comes from heater bands and 80% comes from friction. Universal molding is a language, a global language that combines labeling the equipment and using universal parameters.
What are universal parameters?
These are parameters that can be transferred from one injection system to another. For example, instead of using injection speed, universal molders use injection time. Instead of screw position, they use volume. Universal molding is an organizing committee, a group chosen to be in charge of promoting the MU discipline in their factories, guaranteeing a minimum of 100 hours of training annually. One tool that should be considered is to develop posters for the factory, to be placed in the molding room, the hallways, the cafeteria, or any place that employees gather. This committee should include representatives from all departments: quality control, production, mold maintenance, equipment maintenance, engineering, and sales.
Why universal molding?
Because it can generate great savings for your factory and reduce the time it takes to create good molders. Universal molding recommends the use and maximization of equipment. For example, dryers, water temperature control units, press size, and the size of the injection unit should all be properly determined and adjusted. Our ambitious goal is to develop the best molders in the world and increase the number of precision molders in the plastic industry.